So electron withdrawing groups. Ugh. Yeah, this pen sucks. All right, don't tell my wife I said that about her pen. I'm gonna have to draw with my finger, and it's gonna look like a big fat crayon, but that's okay. Might be okay. So electron withdrawing groups on a benzene ring, okay. There's two kinds. Electron withdrawing groups have a double bond next to the ring. Doesn't matter what the double bond is with, except it has to be something more electronegative than carbon, usually. Okay. And then for other aspects of electron withdrawing groups, things that are good electron withdrawing are things that have, how do I want to do this? Partial positive charge in the benzylic position. Okay. So if you think about what kinds of things those are, those include nitro groups, right? Nitro is really good because it has the carbonyl-like group with a double bonded oxygen, and it has a positive charge, and it has the two oxygens, which are more electronegative than nitrogen, that make it really positive. That's why that's such a strongly deactivating functional group. And then other kinds of things that fall in that classification are things like this. And as far as deactivating electron withdrawing groups, right, that's strictly by induction. And that turns out to be a really strongly deactivating group. Okay. So carbonyl groups are generally moderately deactivating, and then everything else that I've drawn up there is really strongly deactivating. Turns out I don't have to look for my finger, it's on my hand. Sorry, it's just a comment about always looking for my stylus. Weak deactivators are things like fluorine. Okay, that's not good for that though. So when fluorine's attached, even though fluorine's strongly electronegative, it has a pair of electrons it can donate back through resonance, and that's what makes it a weak deactivator. Okay, so then good so those are electron donating withdrawing groups, electron donating groups. Anything with a lone pair on it. Okay. Good ones are. So benzene. Oops, didn't like my finger. So that's a good, or what they would say moderate. Weak activators. Would be things like just straight alkyl group. Okay. So the best, what are the best? Best activating substituent is probably like a nitrogen with a lone pair on it, because the electronegativity of nitrogen is lower. Okay, but really it's can donate electron density, so alkyl groups, lone pairs. Those are activators, right? Electron donating groups. Things that are deactivators or electron withdrawing groups have double bonds next on the benzylic carbon, also have very strong inductive effect on that carbon, like on the benzylic position, like the nitrogen in the nitro group, or the three fluorines on the carbon of that trifluoro group. Okay? Good? So let's go over some energy diagrams. Somebody asked, what is the rate law like for these reactions? And to do that, you need to look at energy diagrams. And to do the energy diagrams, you have to draw the mechanism and talk about it a little bit. Okay, so orthonitration of chlorobenzene. Now, so here's Cl. Draw double bonds in like this, right? And then I'm not going to draw the formation of the nitronium ion. I'm just going to use it. So energy diagram, right? You've got to go through all the steps. One, that's one step in the mechanism. That forms, actually I think my finger works better than a stylus. I just don't like drawing with my finger. Now, at this point, you could draw that sigma complex is what it's called, okay? So I'm going to draw this over here and call this the sigma. I'm just going to put sigma over here. You can draw the sigma complex. But in the energy diagram, that sigma complex, right, these are the resonance structures for it, is just a single compound. So there's no activation energies in the sigma complex, okay? So now, this next step is the minus H plus caused by the base. And that will form the product. Dang it. Oh, I lost my chlorine group, sorry. There's a Cl up here. I'm like, I knew there's something up there, but I don't know where it went. So that already formed the product at that point. Okay, so energy diagram. Oh, sorry, hang on just a sec. We gave it the office. Oh, this is the office. Sorry, So at the bottom, this is the reaction coordinate. On the right, we have energy or free energy. Here's my reactant. Reactant and product are not that different in energy. Okay. But going to be a little bit lower. So what happens? This first step, right? In the first step, you have to form this carbocation. So as far as energy goes, that's the highest activation energy of the two bumps that you'll have in the curve. Then the next step is this removal of this proton to form the product. What do you think about the energy of that? Low, because it goes back to being aromatic once you remove that proton. Okay? So you're going to expect this bump to be low, and then it'll drop back down to like this. So that's probably what the energy diagram looks like for this particular reaction. It's got two humps. The first step is the rate determining step, and it involves both the nitronium ion, okay, and the chlorobenzene. And I'm not including the step for forming the nitronium ion. I'm just assuming that it's formed in solution. If you had that, that would be another step. But I don't know where that actually falls in relative terms to this. So what else is there about this? So that means the first step involves two molecules, so it's a bimolecular rate law. So you should be able to change the concentrations of both and see a change in the reaction. Although the nitronium ion, you have a harder time controlling what its concentration is. Temperature dependent on the concentration of nitric and sulfuric acids. It depends on a lot of stuff. Let's do meta-nitration of chlorobenzene. And I'm going to draw the mechanism out, and then I'll go back to the other drawing, okay? And what I'll do is draw in the comparison on top of the other energy curve, okay? So let me go back to this drawing, and I'm going to make another page here. So this is now meta. Oops, I hit the button. I'm going to call this meta-nitration. And so in the meta-nitration, it goes like this. Just my Cl. I'm putting the nitro group here. Oh, sorry. Let me actually draw the mechanism. So I have the nitro group like this. And that gives me this guy. And again, sigma complex. Now I'm going to come back to this in a second. Okay? But at this point, base can come along, take that hydrogen, put that back. I'm at my product. And this is NO2 down here. Sorry, I ran out of space, but you get the idea. And up here's the sigma complex. Okay, question. How many humps in the energy diagram? All right, how many arrows are there? There's the 2, not including the sigma complex. Which is the biggest step? What is the biggest step? First step, making a carbocation. Anytime you violate the octet rule, it's a big deal, right? So that first step. So let's go back. How is it going to be different from this one? As it stands, it doesn't look like it's any different at all, right? It's 2 humps, first step's bigger, second step's small. Products are going to have about the same energy. Meta might actually be lower in energy because there's less sterics involved. The 2 groups are further apart. So the question is, right, if I overlay the energy diagram for this one versus, versus this one, right, turns out, I keep doing that, sorry. Turns out, this is ortho. That's what meta looks like. So this one's meta. So now we have to, what we're going to do is I'm going to draw the carbocation intermediate for both, and we'll look at them and see like why, and talk a little bit about why the meta is higher in energy than ortho and para. Okay. Okay. So one intermediate. Looks like this. The other intermediate looks like this. Okay, so a couple of things. This positive charge that you see here can jump around to positions, right? From here to here to here. Do you guys see that? Just by resonance, I can get the partial charge, the positive charge can be here and here. For the ortho, and for the para, it turns out, so I'm not going to do the para, where the charge is going to show up on this ring, if this is 1, or this is a top position where the charge is going to show up. They're going to show up down here, right? Down here. So I can get a positive charge here and here. All right. Now, this chlorine, right? Same thing would happen if it's fluorine. This chlorine is pretty electronegative. It's one of the more strong electronegative elements. So one of the arguments that you could make is that it would draw out electron density and make the reaction slower. Just because it can draw electron density out because of its electronegativity. But the other thing that the chlorine has going for it is it has lone pairs. Okay? So the chlorine can donate electron density back through the lone pairs, but it pulls electron density out because of its electronegativity. And so it turns out what happens is, if you look at this other structure, the meta addition, right? This chlorine can never stabilize this positive charge. So as a result, that's why in that energy diagram, the energy for the meta position, right, adding to the meta position, that intermediate is so much higher. It never gets stabilized by the lone pair. So here's the thing. Chlorine, the halogens are the exception to the idea that all ortho para directors are activating, right? It's kind of the exception to that, because it turns out halogens are all ortho para directing because they can stabilize this intermediate. But because of their electronegativity, they're all deactivating. So they slow the reactions down. Okay?
So none.
They're weak deactivators, though.
Oh, so it's because of the lone pairs and because it's in
Yeah, so it's like it's right in the middle. Like you could have called it either way, and the way we call it is based on what the product of the reaction is and whether it goes faster or slower than benzene. So all these reactions go slower than benzene. They're all ortho para directors. Okay. So yeah, on that chart it's to the left, I think, that I drew. Okay. So let's go. I like these next slides. This is kind of like a review. Survey of strong activators, moderate activators, what makes them moderate. Okay. So these are all strong activators. What makes them all strong activators? Donate electron pair directly. Okay, now, excluding this one, okay, which do you think is the strongest activator? Excluding the anion, which one's the strongest most strongly activated? Okay, so first of all, nitrogen more so than oxygen. Why? Less electronegative, right? So this argument about withdrawing electrons by electronegativity and donating back. Nitrogen doesn't draw the electrons back as hard, but is the same size as carbon, so it donates electron density very efficiently. And it's less electronegative than oxygen. Now, if you look at these three, right, what do R groups do? Donate electron density, right? So it makes it easier for the nitrogen to donate the electrons. So as you're looking in the order here, this is increasing reactivity, right? So from left to right, excluding this one, it's very easy to see, right, increasing activity going to the right. I actually don't know where this falls in relationship to this, because it is probably not that important. That is the oxygen O minus versus the nitrogen. But having said that, if you look at O minus versus OH, which do you think is more strongly activated? O minus, because it has more electron density and wants to donate more, right? So, excluding this one, right? What's true about all the moderate activators? What's that? They all have, do you remember the analogy I gave you about the dating? Sorry, did I give you that analogy? Right? This guy's dating 2 electron acceptors, so he clearly cannot donate his electrons as efficiently to both. I know it's like organic chemistry dirty talk, but you know, you'll remember it. Yeah, so resonance is split up between these two, right? So strongly, sorry, of the moderate activators, right? This is a nitrogen. Which ones do you think is better at donating electron density? Okay. Yeah, the same trend is generally true going in this direction. Although nitrogen's better at donating electron density in both directions, right? So it's a little bit harder to tell. And adding R groups to it helps to increase the electron density. Okay, weak activators are all alkyl. Weak deactivators are the halogens, because these just rely, weak activators rely on hyperconjugation, right, that through space effect. Weak deactivators, right, they're weak deactivators because not only do they withdraw electron density through electronegativity, but they can donate a little bit back. Okay. Moderate deactivators, same principle applies, right? Actually, these two are switched. They didn't plan to put them in order, but the first two are switched here. But they're pretty much in order after that. This, right, electron withdrawing by resonance versus this. Well, this one is less strongly deactivating of the moderate deactivators because this pair of electrons here contributes to the carbonyl and makes it less withdrawing from the ring. Okay? Because it's splitting time. The carbonyl is trying to take electrons from both the ring. It's also trying to take electrons from the oxygen, so it's splitting its time there. Let's see, what else is there? Are those switched too? I think those are switched too. Well, that's okay. Doesn't have to know exactly what the order is. Again, here, right, deactivating because of the carbonyl, not as much as like one of these would be because the pair of electrons on nitrogen contributes to this double bond, making it less deactivating to the ring. Okay? So think about it as a competition. And the most strongly deactivating substituents are things like these, like carbon with 3 halogen groups on it, nitrogen with 4 alkyl groups on it because it's going to have a permanent positive charge, okay? And then nitro groups. Okay, we talked a little bit about directing substituents already. Let me see real quick. Yeah, so let me make one other comment. Okay. If it has a lone pair, it's next to the ring, it's always ortho para directing, regardless of whether or not it's activating or deactivating. Okay. So if there's a lone pair adjacent to the ring, it's always ortho-para directing. If it has a carbonyl group next to the ring, right, it destabilizes the ortho and para positions, so it always ends up being meta directing. It doesn't make the meta position more stable, it just makes the ortho and para positions less stable. Okay? But again, in summary, carbonyl group next to the ring is a meta directing substituent. So even if you get a substituent that you've never seen before, like this one, right, you can predict whether or not it's ortho-para directing or meta directing. So you look at this, right? That nitrogen, what is it? It's ortho-para because if you draw out the structure completely, that nitrogen has a pair of electrons on it. So you might have to go back in, put in 2 gigantic dots for electrons. And now you know that this is electron donating this way. It's not as strongly an activator, an ortho-para director, let's say, as maybe an amine would be, or an NH or NR2, right? Because of that carbonyl group, but it's still an ortho-para director. Okay. Now, we've done, like, if I asked you how this was made, don't worry about the BR2 part, but if I asked you how was this made, this nitrotoluene, okay, what would you have done? What group went on last? The nitro group went on last because they're in ortho-para direct. That means the ortho-para director was there before the nitro came on. Okay. If these had been in the meta position, then somehow the methyl group would have been added last, right? And the nitro group would have been added first. Does that make sense? So the orientation of the groups is telling you what the last group was that was added on. So now we have kind of a different problem. The problem is we have 2 substituents and we're trying to add a third. Okay? So what you have to do is you have to consider the directing effects of everything that's on the ring and see how they work in concert with sterics. Okay? So, for example, oh, and actually, I'm getting to one of the questions that somebody handed in last time. I didn't have time to like type it all up, so I'm just going to talk. I'll address it directly when I get there. So, well, let's do this. I am going to draw in one color for the methyl group. So that's the methyl. Methyl is what kind of group? It's a donating group, so what kind of directing group is it? Ortho-para. So it can go here, right, or here. Right, so when you do a bromination, if it was just the methyl group, it would be in the ortho or the para positions. Well, the nitro group is already in the para position, so it's not going to put it there. Okay. On the other hand, what is the nitro group? Yeah, so nitro is meta. So meta to nitro is actually in this position here and here. Right? So in this particular instance, these 2 functional groups on the ring are working together, so you can guess that the major product we'll have CH3 at the top. Nitro group at the bottom, and a bromine ortho to the methyl group and meta to the nitro group. So in this case, it worked out well because they worked together, right? Okay, so this is a nitration experiment. Now you notice you have ortho-paras, right, directing, and you have meta-directing. I mean, sorry, you have 2 ortho-para directing groups. Sorry, we don't have a meta-director. We have 2 ortho-para directing groups. So, in other words, there's a conflict in these positions in that this is ortho to the methyl group. That was ortho to the OH group. And the second one is ortho to the methyl group, right? So you really could have two products because those are both ortho para directors. The product you get is which? And give me the reason why. Ortho to the OH because, yeah. So both of these stabilize a carbocation, but the OH group is the strong activator, and then the CH3 is a weak activator. So in terms of what product gets formed, this would be the product that gets formed. The one that is ortho to the stronger, or is positioned, more generally, positioned based on the stronger activating functional group. Hey, another example. These are both ortho para directors, right? One of these is going to be major, and one of these is going to be minor. Almost always you get mixtures. Both are moderately activating. Which do you think the major is?
On the right. Or the left.
The one on the left. Why the one on the left? Steric hindrance. So, like I said, you know, when the group is small, like you have a methyl group, right? Generally, it's like half and half or a little bit more in the ortho position. But as soon as it gets bigger than like methyl, then the para product generally becomes the major product. Okay. Well, in this case, the para products are blocked, right? So, but what that is an indication of is that the sterics plays a big part in where the substituent ends up. So you're going to end up primarily with the major product being in the ortho position simply because of sterics. Okay, so, sorry. So, new compound. I switched. It was the left one. This is the major. That's the minor. I got ahead of myself. I saw major on the left and minor on the right. So that must be the answer slide. Nope, it's not when I put it up. Okay. So now what we have is we have orthopara directors, right? They're meta to each other. There's one product that's missing here. You know, it says the major is the one on the right, the minor is the one on the left. Sorry, I should say it like this. The minor is the one with the nitro group on the left. The major is the one with the nitro group on the right. Why is that again? Away from the large substituent. And you notice this position, right, is para to this and ortho to this. The minor position, right, that's this here, is para to this and ortho to this. So both of those positions are favored. What's the one position that's favored that you don't see a product for? Where the orientation is favorable, yet I don't have a product drawn up there. The one right between, because that would be ortho to both. Why don't you think there's a product there? Same reason that the major product's the major product. there's so much steric strain to get another group in between the groups that it just doesn't form there. Okay. So really, not often do you see a substituent added between two other substituents if one of the other positions is available. Now, if I had had 3 here, then and made some steric strain down here as well, then you might have seen some of this form, but the reaction would be slow because it's just hard to get it in there. Okay, so here's a tricky one. I'm going to draw it on the board. I don't want you to have the answer. Let's say you wanted to make this ortho bromo T-butyl benzene, okay? How would you plan the synthesis? Because you notice these two groups, right, are next to each other, but one of these groups is really big. So the result would not, if you did the synthesis and you said, well, I'm going to do the, it doesn't matter which way you do it, but let's say I'm going to add the T-butyl group on first. This is one of those instances where alkylation might be used. So you would take T-butyl chloride and catalyst, like aluminum chloride. And then you would get this. And then you would do a bromination. And you'll get 2 products, right? So one product would be this. The other product will be this. Now, regardless of how you do this, one of those is always going to be the major product because one of the reagents is so big. Which one's the major product? Para, because it's so big, it's going to want to place it far apart. So this, regardless of how you do it, this is major. So it turns out from benzene to this ortho configuration with a large group is not possible, okay, unless you do some modifications to the ring first. So the classic modification for this, what that they teach all the time, this is how you do it, okay, is first, if you think about the synthesis and you add one step here, add one step here, okay. And then you add what's called a blocking group. Well, that's what a lot of people call it. It's really a protecting group for the pair position. It's to keep something from adding there. So what you do is you add something there, right, so that the only position that's available is ortho, and then you remove it. Okay. So the blocking group could have either be ortho-para-directing or meta-directing. Which one would you choose? What's that? Meta, right? Because if you make this a meta-directing group, it directs it to this position and not to here. Okay? So slows down the reactions here by its resonance structures or the instability of its resonance structures, allowing this to be faster. And this group helps to make this to be faster as well. So the standard group is a sulfonyl group, SO3H. which you can add through sulfuric acid. So here's the concept, right? T-butyl group, install the blocking group. You could have added the bromine first, but the problem with bromine and adding the blocking group, why don't you do the blocking group with the bromine on first? Because it's also ortho-pairs, right? Blocking, because bromine's small, the blocking group, there'll be a substantial amount of blocking group in the ortho position then to the blocking group. So that's not so good. Right? So you have the T-butyl group, put the blocking group on the end, that's the sulfonation step. Then you brominate, and then you remove the block. So those are the standard steps when you have two groups next to each other, even though they're orthopara, and there's like one's really big. You can't work around it. So we talked about sulfonation before, and I mentioned this. I just said, oh, this will come up later. Well, this is the later. Okay. Sulfonation is reversible. So if you do it, it's like a Le Chatelier's principle kind of thing. If you do it in the presence of concentrated sulfuric acid, you drive the equilibrium to the right. And if you do it in the presence of dilute sulfuric acid, you drive the equilibrium to the left. And the sulfonate likes to leave the benzene ring under those conditions. Okay, so we have a lot of synthetic strategies. I like all these charts, but it's hard to talk through them. But we use this as a point of reference, okay? Exam in when? Not this Tuesday. Right. The following Tuesday. This is a list of the reactions that you have to have. Now, having said that, what you should do is write the electrophilic aromatic substitution reaction mechanism once and then just draw all the mechanisms for making each of the electrophiles. Okay? And then we also talked about some of these things, but we didn't always provide mechanisms for these ones. But once you have like an acyl group, alkyl group, or an acyl group on there, or you have nitro or sulfonate, oh, we didn't do sulfonate removal on this chart, but you can do other modifications with these as well. So like nitro groups can be reduced. Acyl groups can also be reduced. And then alkyl groups and even acyl groups can be further oxidized. Okay, so there's a lot of modifications that you can do. To oxidize an acyl group with what we've been doing, though, you have to reduce it first and then oxidize it. Just say that. Okay. So we're going to make three, we're going right to the, what we can do, let's do the 3-nitrobromo-benzene. I think we did that one already, though. Hang on. But yeah, let's do the next one. We already did 3-nitrobromo-benzene. It's one of the first examples. 2 directing. So we're going to do 3-chloroaniline. So we want to make this. Sorry, wrote the answer already. So I have a benzene ring, a Cl, and I have a aniline, like that. How would you make that? What's wrong with the picture? usually what you do is you look at the orientation of the substituents and you say, oh, well, they're meta, so I put the meta director on first. So what's wrong with the picture? There's not a meta director on there, right? So that tells you, since that is not an option, that you have to do a transformation of one of the functional groups during the course of the reaction, okay? So the first thing that you might think about doing is, how do I make one of those a meta director? Well, there's not much you can do with the chlorine, but with the aniline, right, that could have been a nitro group. And if it's a nitro group, then it's a meta director. Okay? So, you know, the normal process orientation determines the first group added. Man, this thing's just writing so slowly. But these are both meta directors, so you don't have that option. So now you have to think about, okay, not an option. Then you have to think about changing functional groups so that it is an option. It's functional. To get proper orientation. Okay. So in this case, they're in the meta position. But both are orthopara, right? So that means you're going to change one of the functional groups to meta director. I should say from a meta director. You're really not changing it to in this case, but I'll still say 2. This is in your analysis. Okay, I was supposed to say meta director, but that's all that I was tired of erasing and rewriting. That's all that the network picked up off my finger. So that means the step before here CL was that amine must have been nitro. And that's an easy conversion. Okay, so that's the retrosynthetic arrow, so I'm working backwards. Before that, you would have had the nitro group on there. And you would have added the Cl to that. And so then the first step in this whole process is to add the nitro first, And so we've worked all the way through, and now you can write it in the forward direction and put all the reagents in, okay? All the reagents having been on that previous slide, so you can fill that stuff in. Questions? Handwriting interpretation? Meta director. Sorry. So, a couple things. This is a nice little chart in your book, right? Functional group conversions that change directing effects. So one is the one we just talked about, zinc, right? Amalgam and HCl make meta-director, ortho-para-director. Oh, actually, that's just zinc and HCl, sorry. And this one, right? Zinc, mercury, amalgam, carbonyl group, meta-director into an ortho-para-director as well. So you take a carbonyl group, right, clip it off, and now you have ortho-para-directing. You can go the other way. These are ortho-para-directors. You can use permanganate under basic conditions, or you can use dichromate or chromic acid Jones reagent, and you can make an ortho-para-director into meta-director, or you can do bromination, allylic, or it's like benzylic, right? But allylic bromination. Just replace all of these with halogens, and now that's a meta-director. So again, where things end up in the end, if it's not obvious from the orientation on the molecule, then you have to think to yourself, something must have changed between when I added the first group and the second group. Okay. So a couple limitations. If you try to do this, it won't work. For a couple of reasons. But the primary reason is under acidic conditions for nitration, that becomes a deactivated ring. So the best thing you might get is a meta addition, right? Because once you do this under acidic conditions, which is the conditions for nitration, then this becomes NH3 plus and becomes deactivating on the ring and meta-directing. Other reactions, though, like bromination, don't work very easily for products like this as well, because the aniline ring is so active that you can't stop it after adding one. You just end up adding more and more and more and more. Okay. If you're doing Friedel-Crafts reactions, right, either acylation or alkylation, they're both very sensitive to deactivating substituents, so there's no reactions with those. Okay. Okay, let's do a little practice. Let's say you want to make that, okay? How would you make that starting from benzene? You could have any other reagent you want other than the product. You can't just add the product and say, here, I made it. Hey. So how do you make that? Start from benzene, right? But let's analyze this product. So I have a benzene ring, but I have these on them. Where do those come from? Yeah, it's like a Jones reaction, right? With a sp3 carbon that has hydrogens on it. So you can think of it as the thing before this. Okay. Had that. So now you have to think about how do you get the R groups on there? There's actually like a really kind of cool way to do it. What's that? Yeah, you could do an alkylation reaction, but the only problem is you'll also get some R group that's down here, right? But really what you want is an alkylation reaction and end up with the R groups in the ortho position to each other. So this, I'm showing you, this is a standard trick, okay? Make sure these are connected when you do it. So if the carbon chain, like if the total number of carbons you're adding is like 4, right, then you'll end up making another 6-membered ring. So your reagent that you do this with can be something like this. And you don't care about rearrangement as much, because even though it can rearrange, you're just going to cleave it off in the end, so it doesn't matter what you really attach to there as long as it's a hydrogen, okay? So oops. Really the thing that you're going to do is just something like this. You add them both at the same time, and then that back step is going back from here to here is just Jones reagent. Okay, so I'll write it all out in the forward direction so you can see like how you put it together. So start with benzene. And then we're going to do, let's see, 1, 2, 3, 4, 5. Let's do 4. 1, 2, 3. And then aluminum chloride. Turns out the product you'll get from this, and I'll do this in a different color so you can see it better. It's that. But not the ring, right? Not the circle in the middle. It's a ring, but it's a Friedel-Crafts reaction. This goes to here, and then this goes to there. Because it's only 4 carbons long, right? It's probably going to form like that. It may make some of the one where there's some rearrangement and you get a 5-membered ring, but most likely what you'll get is a 6-member ring because it's the easiest conformation to get into. Well, that's not always true. 5-member rings form very quickly. And this is just Jones reagent. Or permanganate under basic conditions. And you heat it. All right. Let me think here. Yeah, it really took my time, actually. They covered a lot of material, but I just went into a lot more detail. I'll probably have to do one more lecture on this. But I think the practice is good, right? Practicing more molecules built better. I don't know. I'll leave it up to you guys. So we're going to design a synthesis for this one. So now we have to sort of work backwards, right? What do you think the last group added is? Nitro group, right? Why the nitro group? There's a couple of reasons, but this is ortho pair directing, and this is meta directing, right? So they both point to this position. If this was the last group that was on, that's meta-directing and that's meta-directing. And if this was the last one put on, you wouldn't get it on because this is both deactivating functional groups. And this would be an acylation reaction. So this one is the one that makes the most sense. You just start with one and say, if I had added that, how would I have put it on? And then look at the functional groups that are there. Okay? If I'd added this one, how would I have put it on? And you have to think about all the limitations as you go along with this. So it makes sense that the nitro group, that's the last one that was put on. So now what you have to do is you have to put the two groups on here, right? And Friedel-Crafts acylation reactions are sensitive to deactivating functional groups, but bromine, the halogens, are not deactivating enough to stop it. So if you look at these two, that's one of the limitations you'd have to think about, though. That's a meta-director, that's an ortho-para-director. They're para to each other, so the bromine had to have been there first. You put the bromine on, right? Then you do the acyl group. And then you have to do the so you have to do the nitration. So that's the working through of that synthesis. So this is the, now starting at the beginning, okay, with a benzene ring. Do the bromination first. Then you can do the acylation. Once you have the acylated product, then it's just a nitration reaction. After that. But again, start with the product. Try to figure out how each one of those things would have got added. And again, same thing that happened before. If there isn't an obvious way to do it, then you have to consider like functional group was modified during the course of the process. And then it gets more complicated, right? Because you have to guess at what that might have been. Okay. So, yeah. This is known, okay. Electrophilic aromatic substitution, done. Okay. New mechanism. This is known as a substitution, nucleophilic, so not an electrophilic, okay. Nucleophilic aromatic substitution. Now, that might sound like, it doesn't sound right. Right. To get a nucleophile to attack a benzene ring, we've learned about SN2 reactions, right? SN2 reactions are backside attacks. Where is the backside for every single one of these carbons? Yeah, they're sp2, right? But if you were to attack, like you think nucleophilic, because what we learned is like SN2, right? SN2's backside attack. If it's a backside attack to replace this bromine with an OH group, I mean, it doesn't make sense. The backside's in the middle of the ring. It can't even get close to that. But it's sp2. It's flat. So when you get a nucleophilic attack, it can come from the top side. It doesn't have to, the reason it's a backside attack in an SN2 reaction, that's the available space for the nucleophile to come in. But when it's sp2 and it's flat, then the availability of the p orbital that's going vertically is there. You can drive in from an angle from the top or the bottom because it's a flat molecule. But still, like benzene, is not really amenable to this kind of reaction because it has that electron cloud. The nucleophile would have to penetrate the electron cloud, which is like questionable, and get to the carbon and then displace something. Okay? So, turns out this is a very common reaction. Just to say, if this nitro group isn't here, in order to get this reaction to happen, has to be very high temperatures. If I remember right, my numbers right, it's like 300 degrees Celsius, okay, and high pressure. And then you can get an OH group to attach to the benzene ring and displace the bromine. But adding a nitro group makes it much easier. Adding a nitro group makes it so at 70 degrees Celsius in sodium hydroxide, concentrated sodium hydroxide, you can get this nucleophilic a reaction to take place. You don't really have a good leaving group, right? Your nucleophile, well, sorry, in this case you do have a good leaving group. You have the Br2, but you don't always have a really good leaving group, so we'll talk about that. All right. So electron rings, aromatic rings are electron rich or difficult to attack. So we must, in order to make a nucleophilic attack on a ring, you have to make the ring electron deficient. How do you make a ring electron deficient? Right? Strong electron withdrawing. So you remove the electron density and make it easier for the nucleophile to come in. The more electron leaving groups or withdrawing groups that you have, right, the faster the reaction will go. You have to have a good leaving group. When you don't have a good leaving group, it usually is a different reaction. And they have to be ortho and para. The leaving group has to be ortho or para to the electron withdrawing groups. Okay, so let's look at the mechanism. We'll talk about it. So there's my electron withdrawing group. Okay. Nucleophile comes in. Again, it doesn't have to come in from the backside because it's planar, so it comes in from the top at an angle or the bottom at an angle. And then you get this negative charge here. And you notice what happens by resonance, right? That should be going to here maybe and back out to here. But this positive charge stabilizes the negative charge here. So it's important, okay, that when this nucleophile adds, that it adds in such a way that the negative charge that's placed in the ring can be stabilized by the electron withdrawing group. I love this name, Meisenheimer. It sounds like something from like a Christmas story, right? And then that Meisenheimer came along and took every child's money. Okay? That's what I think of. I think of like the Grinch things, Meisenheimer. I don't know what the last name actually means. Clearly, probably German or something. Okay. Now, once you have this complex, right, like I said, usually we show this arrow going to this bond. Important thing is, though, that this structure can stabilize the charge that ends up here. So there would be a double bond here. When this goes back down, this collapses, and then whichever two of these is the best leaving group leaves. Okay. And then you form your product. What makes one of the leaving groups leave? Right? Aromaticity in the product. The product is aromatic. It can kick off that leaving group. Turns out if you do it in the meta position and there's the same conditions, there's no reaction. Let's see. Yeah, we'll stop there.